Hi everyone, so I'm Baptiste Genest. I'm a French graduate student in applied mathematics, and I'm going to talk to you about non-Euclidean sliced optimal transport sampling. And this is a joint work with Nicolas Courty and Coeurjolly. So first, to sum up our contributions, let's say that we contribute to the set of techniques that are able to sample blue noise points with good quality in any dimension, okay, and that use optimal transport to do so. And basically we extend an algorithm that was defined in a simple Euclidean setting to non-Euclidean domains, such as the sphere, the hyperbolic plane, and the projective plane. And regarding the applications, we hope that since you can now sample intrinsically curved manifolds, it is going to be easier to apply sampling to geometry, okay? So first, let me talk to you about optimal transport, okay? So suppose that you have two point clouds, A and B, and you want to move the point cloud A into the point cloud B by moving one particle of A, each particle of A into one particle of B. Okay, so you're looking for a one-to-one assignment. And then if you had to move yourself each of those particles, it would take you some time or at least some effort that could be proportional to the distance that you would have to make. Okay? And so optimal transports basically only ask very natural questions and simply ask the question, well, what is the optimal assignment such that it would take you the minimal effort to move the particles from alpha to beta, from A to B, okay? And so in this case, it's this one. And when you look at this image, it might give you the intuition that in some sense, it defines a very meaningful notion of distance between those two objects. If it is very easy to move all the particles from an object into another, that means that in some sense, they're quite close, right? And vice versa. And so it is precisely what measures the Wasserstein distance. Okay, the Wasserstein distance is between two probability distributions, simply what is the minimal effort that you have to make to move from the particles of the first one into the second one. Okay, and so what is interesting here is that it is defined on probability measures because it is the framework in which optimal transport is expressed. And what is so nice is that, as you know, probability distributions can be both discrete or continuous. And so that means that optimal transport is going to be able to handle both discrete and continuous data, which is going to be very important. Okay? But so, first, if the Wasserstein distance is so great, how hard is it to compute it? Well, thanks to Coeurjolly, we know that it can be expressed as a linear programming problem, okay? And even though they can be quite optimized, it is still an n-cube algorithm when n is the number of points, okay? And so what is interesting is that optimal transport is hard in any dimension except in dimension 1, where it is absolutely trivial, okay? Because now you have simply two lists of numbers, and all you need to do to find the optimal assignment is to sort those two lists and to assign the first point of the first list to the first point of the second list, etc., etc., okay? And so as you see, it is very easy to compute and gives you a simple n log n algorithm since you just have to sort two lists of numbers. Okay? And so, if optimal transport is hard in any dimension, except in dimension 1, one very natural idea was to say, well, maybe I could transform my ND optimal transport problem, which is hard, into a bunch of 1D optimal transport problems, which are going to be way easier to solve. And this is precisely the idea behind sliced optimal transport. Okay? So, like, suppose that you have your two point clouds, and instead of solving the global problem, you could pick a slice, a direction, okay, project your points onto that direction, solve the optimal assignment along that direction, and repeat that process many times, okay? And now, if you take the average of the Wasserstein distance along all those directions, okay, it will converge, thanks to the law of large numbers, to this integral, okay, which is the integral of the Wasserstein distance along all possible directions, and we're going to call that integral the sliced Wasserstein distance, okay? And what is so great about that is that, thanks to this Monte Carlo approximation, it can be very easily computed, but it is a very good approximation of the Wasserstein distance. There are many theorems that tells you that you have like a bounded complexity if you can control the Wasserstein distance by the sliced Wasserstein distance and vice versa, and that the sliced Wasserstein distance induces the same topology as the Wasserstein distance, etc. And so it is really a good approximation, but that is way easier to compute, okay? And so I talked to you about that you can both define optimal transport between discrete and continuous densities, but what is of course, we see that since in the discrete case, since we only have to sort the points, it is very easy, and so we would like to remain in that simple setting. And well, instead of handling directly continuous densities, which are very hard to define and to define the projections, etc., and well, we can simply approximate our continuous densities by a large number of samples and simply solve discrete to discrete problems, and it will converge to the same result. Okay, so it is very easy to compute, and by default, it doesn't depend on the dimension of your densities, which is really nice. Okay. And so, okay, so optimal transport sounds great, but how do you make a link with the blue noise sampling problem? Okay, so if you look at those two point clouds, well, even though they both have the same probability to be drawn from the uniform distribution, of course we prefer this one, okay, because this is typically what we would call a blue noise point cloud, right? And what we don't like about this point cloud is that there are many clusters of points and many empty spots, okay, and those are really bad for numerical integration. Okay, and so to sum up, we feel that in some sense mu2 is way closer to being uniform than mu1. Okay, in some sense, right? And what is really nice is that it is precisely what measures the Wasserstein distance. In the sense of optimal transport, mu2 is way closer to being uniform than mu1. Okay, and so once again, a very natural idea. Well, obviously mu1 is way easier to generate, right? Because all you have to do is to sample the point. Okay, but you could start from mu1 and optimize it step by step by gradient descent to minimize its distance to the uniform distribution to get mu2, which is a blue noise point cloud. Okay, so very natural idea, and this is precisely the idea behind sliced optimal transport sampling. Okay, so it is basically a stochastic gradient descent on the distance from your distribution and the uniform distribution, or actually any distribution that you would like. And so to do so, we need to be able to define the gradient of the transport energy along one slice. Okay, so if the distance is simply the quadratic distance between 2 points, well, then obviously the gradient is the difference between your point and its assigned other point. Okay, so it is very easy to compute. And now, when you have your 2 point clouds, well, as in the sliced optimal transport problem, you can simply project your points along that slice, solve the optimal assignment problem, and then instead of simply computing the Wasserstein distance, you can store for each point one gradient along that slice. Okay, and then you can repeat that process many times. And as you see, we are accumulating a bunch of gradients per point. And then, as we do in stochastic gradient descent, you simply take the average of those gradients. And once again, thanks to the law of large numbers, we can show that it will converge to the true gradient of the slice Wasserstein distance. And then, since we want to do gradient descent, we can simply move those points in that average direction, and that gives us one iteration of the descent. And when you repeat that process, it will converge very fast to a uniform distribution, as you see here. Okay, and so it is very simple to compute, works for any dimension, for any densities, etc. So it is very, very nice algorithm. Okay, and so now our contribution is to say, well, we did not invented the slice Wasserstein distance on the sphere and the hyperbolic plane. It was the work of Clément Bonnet and others. Okay, but so what we do is simply taking this algorithm and extending it to those two domains. Okay, and the projective plane as well. Okay, so first, because this is precisely what we do, I need to talk to you about optimization on manifolds. Okay, so suppose that you have a function defined on a manifold, for instance here a sphere, and well, one could still define a gradient, and the gradient of the function at a point would be defined in the tangent plane of the manifold at that point. Okay, but then it asks a first problem, right? Since we are going to do gradient descent, we are going to move in the opposite direction of the gradient. Okay, but as you see here, if I simply move in the opposite direction of the gradient, I might leave the manifold, which is really bad, right? I want to be able to do optimization while remaining on my manifold. So I would need a way to move on the manifold, for instance, by following a given direction, okay, because I want to go into the opposite direction of the gradient. And so it is precisely the role of the exponential map, which tells you that if you are at a point x, you can follow the geodesic that has initial velocity the given direction. And for example, to do Riemannian gradient descent, you can simply iterate that process and repeatedly go, like follow geodesics that have as initial velocity the opposite direction of your gradient. And as you see, as in the Euclidean case, we are going to converge towards a local minimum of our function. Okay? And so that's nice. So that fixes our first problem, and that gives us a way to move on that manifold. And then the other problem is that, as we saw, the gradient of the size versus time distance is the difference between 2 points. But you might imagine that it is not well defined. Like if you take it doesn't make sense in the general case to take the difference between 2 points. But and as well, as we saw, since a gradient must live in the tangent plane, there is no reason that if you take the difference between 2 points here, for example, it would give you something that would live in the tangent plane. Okay, and so we would need kind of the opposite of the exponential map. We would need a function that tells you, well, if I'm at x and that I want to go to y, what is the direction that I should follow to be able to reach y? Okay, and so it is, as it is the inverse of the exponential map, we're going to call it the log map. Okay, and it tells you precisely that. If you're at x and that you want to go to y, here's the direction that you need to follow to reach y with the exponential map. And as you see, when we compose those two functions, we go from x to y while remaining on a manifold. So that's great, and that gives us all the ingredients that we need to be able to extend the algorithm to this setting. So here is the Nizot algorithm, right? For the sake of simplicity, let's suppose that you have only 2 points, defined here on a sphere, but it would be the same for the hyperbolic plane or the projective plane. And so first, Clément Bonnet and others decided that it was a good idea to replace those straight lines, those directions, by slices, okay, which are going to be geodesics, and in the case of the sphere, it is a great circle. So as in the Euclidean case, first you project your densities onto that slice. Okay, then you need to solve for the optimal assignment in 1D. And so on the sphere, it's kind of problematic because we know that the optimal assignment will be by sorting the points, but since they are now defined on a circle, which is a periodic space, it doesn't make sense to sort the points. But actually, all you need to do is find the right place to cut the circle into a line, so that then you can simply sort the points and find the optimal assignment that way. Okay, and the algorithm to find the place to cut is very cheap to compute and doesn't change anything. Okay, so suppose that you have now computed that the projected version of x must go to the projected version of y. Okay, now we would need a way to transmit the information to x that he needs to go into that direction and by that given amount. Okay, and so here's the only tricky part, but we found out that actually we can exploit the very strong structure of the sphere and the hyperbolic plane, because there are many groups that can act on them. And for example, on the case of the sphere, you see all you have to do is find the rotation that's mapped that point to that point, and so it is uniquely defined by those 2 points along that slice. But then it is defined on the whole sphere, and you can apply it to x. Okay, and so now we can simply say to x, well, you need to go reach that point. Okay, so that you would minimize the difference about energy if you were to be projected again on the slice. Okay, and so the gradient is simply going to be, well, the log map between the point x and where it should go according to that group action. Okay, and so that is great. That gives us one gradient, and when you're going to take multiple slices, you will accumulate the gradients, then you will take the average and go into the average directions with the exponential map. Okay, and so that would give you one iteration of the Nizot algorithm, and as you see here, it will converge very fast to a blue noise sampling of any distribution defined on the sphere, the hyperbolic plane, etc. And as you see here, but you can check the paper for more details, we have very precise ways to show that our sampling is of good quality. For example, here we show that we are very good at catching low frequencies of the function, which is really great for numerical integration. And even though, as you see here, there are many sampling techniques that give insanely good results, well, the only thing is that we are defined in any dimension and for any density, which is not the case for any of the other methods. Okay, so it is really where we kind of pay the price of generality, but we can do a lot of very interesting things. Okay, and so I mainly talked about the sphere, but it is also defined for the hyperbolic plane, and all the formulas that we use are closed form and are quite easy to compute. Okay, but you can check once again the paper for details. All right, and so an interesting contribution is that it is known, for example, that that algorithm, when you have very distorted densities with densities of very strong, very concentrated and almost zero everywhere else, well, it is known that there are going to be those weird alignments that are going to appear. And actually, with a simple analogy with statistics, as we know that the median is a way more robust estimator of than the mean, well, by simply replacing the mean of the gradients to get the descent direction, you can simply, if you replace that by the geometric median of the gradients, that gives you a way more robust descent direction. And as you see, it is a very simple fix. It costs basically nothing to compute because we only compute among all the gradients for 1 point. So basically, if you have like 32 slices, it is computing the geometric median of 32 points. So it goes very fast. And as you see, it completely breaks those regularities, which are bad for numerical integration. Okay. So it is a very simple fix to an interesting problem. Okay. But so now we can dive into the applications. Okay, so the first application, which was our motivating idea, is that you might know about the discrete uniformization theorems. Okay, that tells you that depending on the genus of your mesh, there exists a conformal map that will map your mesh either to the sphere, when you have no holes, and if you are more than one hole, there exists a conformal map to the hyperbolic plane. Okay, in the case of the sphere, it is absolutely straightforward to apply your algorithm. You can define any density on the mesh, map it to the sphere, sample it using our algorithm, and map it back to the mesh. Okay, and so it is very straightforward and it works quite well. But then for the hyperbolic case, it's a bit more tricky. Okay, because even though the conformal map exists from your mesh to the hyperbolic plane, there's going to be way too much numerical distortion in most cases. So it is not possible to use it practically. But we found that thanks to the very interesting properties of conformal maps to the hyperbolic plane, actually the embedding on the hyperbolic plane depends on the mesh of the vertex that you place at the origin. Okay, like you can compute all the metric coefficients of the parameterization of the whole mesh just once, which is a very simple quadratic minimization, which is known as the Yamabe flow. But once you have computed that, you can simply pick a vertex and embed a neighborhood, a patch around that vertex to the hyperbolic plane. And then you can optimize the points on that patch and map it back to the mesh and repeat that process. And what is so nice about that, and I highly encourage you to go check the paper, is that there is actually a very simple way to control that. You can embed a patch by controlling how much distortion do you want to have. And as you see, when you want to map a region that is like kind of very curved, etc., and it is going to be hard to map to the hyperbolic plane, well, you can simply embed a small patch, but that will be of good quality, as you see. But then if you can embed directly a huge patch, but once again with low distortion, then you're going to embed a huge patch and optimize more points. Okay, but in the end, when you repeat that process on many patches that are going to overlap, you are going to optimize the points globally. And the fact that you are only optimizing the points locally makes it way more robust than in this spherical case. Okay. And so it is very interesting and it is really nice to be able to exploit both the properties of the sphere and of the hyperbolic plane. Okay. So that's nice. But of course, the interest of our technique is that since we only go through parameterization, it is purely intrinsic, right? Like there are many other methods, such as based on Voronoi diagrams, that works insanely well. Like they are super fast and gives amazing quality sampling, okay? But what is interesting is that it depends on the ambient space. When we deteriorate the ambient space, when the exterior geometry is really bad, as you see here when we flatten the mesh, well, those extrinsic techniques that work quite well, they completely fail now. Meanwhile, our technique that is purely intrinsic and that doesn't care that the mesh is flat gives exactly the same result. Okay, we have like those pair correlation functions that exactly tells you that the sampling is exactly the same. Okay, and there are previous methods that were able to sample the mesh intrinsically, but they were not able to sample any density on the mesh. Like they were based on a good and fast approximation of the geodesic distance, but they are not able to sample any density. Meanwhile, we can sample any density that is either user-defined or, for example, based on curvature. Okay, so that is really nice. And now one last application, which I find extremely exciting because it appears to be quite new and very interesting for geometry, is the projective plane sampling. Okay, so those questions appear very naturally. Like suppose that you want to sample lines. Okay, well, one natural idea would be like, well, I'm going to sample the direction of my lines on the sphere by, for example, using the Fibonacci sampling, so you get very good points that are blue noise, etc. But now if you look at the lines that are generated by those lines, by those points, you see, oh, there is a problem, right? It is not what we would call a blue noise distribution of lines. And it is simply because the line that goes into that direction is the same as the line that goes into that direction. There is a sign equivalence problem that isn't taken into account when you place points on the sphere. Okay, so the points themselves are blue noise, but they are not blue noise when you consider them with their opposites. Okay, and so basically what we propose is to directly sample the projective plane. The projective plane is precisely the set of objects that are defined up to a scaling, such as lines and many other objects. And so as you see, when you sample it with a very simple modification of the original algorithm on the sphere, you get points that are not blue noise by themselves, but they are blue noise when you consider them with the opposites. Okay. And now, when you look at the lines that are generated, they are exactly what we would expect from a blue noise sampling of lines. Okay. And what is so great about that is that, as you know, for example, we can also like unit quaternions, which lives on the unit sphere, a four-dimensional sphere, they can act on vectors as rotations, okay, by that simple product. But as you see, if you pick a unit quaternion and that you put a minus sign, so you get the opposite quaternion, since Q appears twice in that product, the -1 cancels out and you get the same rotation. So that means that one quaternion and its opposite get the same rotation. So there is once again a sign equivalence problem, and if you do projective sampling on the four-dimensional sphere to sample those unit quaternions, you see that you can sample like a blue noise uniform distribution of rotations. And what is nice is that we can sample actually any distribution of rotations. For example, if you could pick one point of view that you like and get variations around that point of view to get a good view of one point of view, etc. Okay, and there are previous methods that, for example, the super Fibonacci method by Marc Alexad, which takes into account that sign equivalence problem, but even though it is very fast, etc., it doesn't take into account, it isn't able to sample any distribution of rotations. And for a small number of rotations, we can show by showing that if you pick a sphere, that you pick a light, okay, or a camera, that you apply all rotations to the sphere, and that you compare all the scores of the visibility among all rotations. When we show that the variance of the visibility is much more smaller in our case, which means that in some sense we are more uniform than the super Fibonacci for a low number of rotations. Okay, but so what is interesting here is that actually many objects are defined in a projective way. For example, as you see here, we can sample also affine lines by their Cartesian equations, okay, by sampling A, B, and C, because as you see, if you replace A, B, and C by -A, -B, and -C, you get the same equation. And so once again, if you sample the projective plane, here we can get a blue noise sampling of affine lines, etc., etc. And so projective plane sampling appears to be really exciting, okay. And so now, if we want to conclude, we introduced Nicolas, which is a very general algorithm to sample any density in any dimension on the sphere, the hyperbolic plane, and the projective plane with blue noise quality. Okay, and it allows us to intrinsically sample matches. And also, projective sampling appears to be really new and promising for many geometric tasks. Okay, and as future works, well, we might use our sampling on the meshes and the simple structure of the sphere and the hyperbolic plane to intrinsically remesh some surfaces. And of course, one very exciting direction would be to continue this extension to other domains, like Lie groups, etc., which could be really interesting. And finally, we could replace our simple gradient descent by other two methods, which would use some kind of Hessian, etc. And it would be to fasten the sampling. Okay? And so that's it. Thank you very much for your attention. The source code is available online.